Today we will work through hypothesis tests concerning the population mean. We are primarily going to work with a single sample. Suppose we want to test the null hypothesis given by h0, uh, mu equals mu naught, where mu is the true population mean and mu naught is the null value. Then, under the assumption that the population is normally distributed and that the population variance sigma squared is known, we can use the z statistic given by z is equal to x bar minus mu 0 divided by sigma over square root of n to derive a hypothesis test to test the null hypothesis against three possible alternative hypotheses. The n in the formula here is the sample size of the random sample that we use to calculate the test statistic z. What if the population variance is not known? We have two scenarios. If the sample size is known to be large, we can, or if the sample size is not large. When the sample size is large, we will use a large sample z-test, and when the sample size is not large, we will use what is known as the t-test. Let's begin with the large sample z-test for single sample hypothesis test involving a population mean. So the assumption here is that n is large. And in this case, using the central limit theorem, we notice that the statistic x bar minus mu naught divided by s divided by square root of n has a standard normal distribution. We will use this as our test statistic to calculate the p-value. The test procedure in this setting is going to require the following assumptions. We will assume that the population variance sigma squared is not known. We will also assume that the population distribution might not be normal. And finally, the most important assumption being that the sample size n is large. We will not specify what large is a priori. The test procedure will follow as follows. We first figure out our parameter of interest, which is the population mean. The null value will be denoted by mu 0, and the null hypothesis is going to be that the true value mu equals the null value mu naught. The alternative hypothesis can be one of three options: mu greater than the null value, mu not equal to the null value, or mu less than the null value. We will work with a random sample given by x1, x2, x3 up to xn coming from the population, and the test statistic z is going to be defined as x bar minus mu 0 divided by s over square root of n. X bar is the sample mean and s squared is the sample variance. Now, if the null hypothesis is true and n is large, z will have the standard normal distribution. We can use this distribution and the z statistic calculated from sample data to calculate our p-values in the three cases of the alternative hypothesis. When we're working with the alternative hypothesis mu greater than mu naught, we will calculate p as the probability of z greater than equal to z, and the other two cases are as follows. Notice that small z is the test statistic x bar minus mu 0 divided by s over square root of n, where x bar is the sample mean and s the sample standard deviation. Now we can use the p-value and the significance level alpha to arrive at our test decision. We could either fail to reject h0. This will happen if the p-value is greater than alpha, or we reject h0 if the p-value is less than equal to alpha. We would want to understand the probability of making testing errors. Recall that the probability of making a type 1 error is going to be the significance level alpha. The probability of making a type 2 error is going to be a little complicated. However, in this setting, we can use the type 2 error calculations done when the population variance was known. In this setting, we will have to work with a plausible value of sigma. We next move on to the one sample t-test. Uh, in this setting, we are working under the assumption that the population variance sigma squared is not known, that n, the sample size, might be small, and that the population is normally distributed. This is a very important assumption. In the setting, the test statistic will be called the t statistic. It is given by x bar minus mu 0 divided by s over square root of n. And we have seen before that this statistic is going to have students' t distribution with n minus 1 degrees of freedom. The one sample t-test procedure is as follows. We state the null hypothesis h0 given by mu equals mu naught, and the test statistic is calculated as small t equals small x bar minus mu naught divided by s over square root of n. The p-value calculation is going to use the fact that my t statistic has students' t distribution with n minus 1 degrees of freedom, and the p-value is calculated as follows. We have the three cases of the alternative hypothesis: when mu greater than mu naught, when mu less than mu naught, and when mu is not equal to mu naught. Remember, for this test, we need to be sure or have reasonable belief that the population is normally distributed. That is, we are assuming that the random sample is coming from a normal distribution. We next move to the probability of making test errors when we are dealing with a t-test. The probability of making a type 1 error is exactly the significance of the test, that is alpha. Analysis of type 2 errors is a bit involved in the case of t-tests. It's not as straightforward as when we were working with z-tests with sigma squared known. So to calculate beta, which is the probability of making a type 2 error when the true value of the population mean equals mu prime, will involve first estimating the population standard deviation and then setting d to equal mu minus mu prime divided by sigma. Finally, we will be using what is known as a beta curve to estimate my type 2 error when mu equals mu prime. An important aspect of a hypothesis test is the power. So for fixed null value mu 0, the alternative value mu prime, the sample size n, and significance level alpha, the probability of making a type 2 error when mu equals mu prime is denoted by beta mu prime. The power of a hypothesis test is defined as 1 minus beta. Notice that if beta is small, the test is powerful, which is to say that the probability of making a type 2 error is small. Another way of saying this is that a powerful test is going to have a good ability to detect when the null hypothesis is false. Now, suppose we run a hypothesis test and come up with a result that rejects the null hypothesis with p less than alpha. Assume another investigator chooses a new sample from the same population and computes a new p-value. An important question of interest would be, how likely is it that the new p-value will also reject the null hypothesis h naught at the significance level alpha? Uh, Turns out that unless the original p-value was very small compared to alpha, it is not surprising that new sample data would contradict the original test result. A case in point would be rejecting the null hypothesis with p-value 0.01 versus rejecting the null hypothesis with p-value 0.0001 at significance level alpha equals 0.05. In the former case, we would have to be very careful about how we interpret the result of the hypothesis test in rejecting the null hypothesis. All this is to say that we should be very careful when we interpret p-values that are close to the significance level. We will work with a lot of hypothesis tests in upcoming videos, but this is all I wanted to say for now. Take care of yourselves, and I will see you around.